All right, let's go through chapter 4. First thing I'll comment is we're looking at the different type cablings and such in the chapter, and I meant to bring a set of sample different types of cables for y'all to look at today, and they're still sitting beside my door at my apartment, because when I pulled up here I went, whoops, I forgot to bring them. And I had set it specifically at the door to grab as I walked out this morning. It was yesterday when I taught the class that I'd realized, wait a minute, I need that stuff. So I've got a collection of stuff. Probably, I may bring them Monday, I mean. But I'm going to do a recording and show the different ones on Collaborate, and then I'll share that out with y'all, and then y'all can go through and look at it, because the online class needs to see it too, so it needs to be as a recording. So we're looking at this point, network access is what the chapter is about, and so a lot of what the chapter is how are we physically connecting them, of what's the media that we're using. And so they're coming from that in it. It's not as much stuff quite in this chapter as in some of the others, I don't think, to you. So I think that'll work all right. So they talk about that there's a different ones that they're using. They mentioned to you about the wireless access points, which they note there is an abbreviation of AP, but you also see them as WAP, and that's just whatever spots you've got to collect in the wireless signals and send signals back out to your PCs, your phones, etc. And some of them have embedded wireless antennas, like the ones they're illustrating there for you, which actually looks like CIST 6200 ACs. Is what it looks like, is what the picture is of there, because I happen to own one of those, and it looks like that one there. And then you've got plenty of others that have the external antennas on them, and that they could have anywhere from 1 to 6 antennas hanging from them. And so you've got the wireless access point hanging back there on the ceiling, back there in the back of the room, that connects to the school network. So they mentioned that. To talk about the NICs, the network interface cards, which I already told you about, and we looked at the other day. And actually we looked at a wireless one on it, but it could have been a wired one. And talk about that. And then I don't have to get the stuff in a different order. Okay. So then they mention about that there's standards for the media that we're using, including using the air as a media, that there are various standards out there for it, and they mention a number of standard organizations that control that. So that ISO gets mentioned again here, because they set standards for a lot of this type stuff. The TIA, EIA is also mentioned here. Actually, TIA, EIA does a lot of the setting of the standards of what is the cable, and so that if you look on these cables, you'll see that it's actually got an TIA, EIA rating on it, which says this is a 568C type cable, which actually is a Cat 5E. And that's why it uses a 568 pinning diagram to it. And then the ITU That one is actually a European-oriented one. I'm not sure why in the book they put that one in blue there for you. But it is European, more oriented on setting standards on stuff, where ANSI obviously sets standards for in the U.S. And ANSI is actually a division of and a member of ISO. Then they mentioned the IEEE. IEEE sets a number of the standards of how things are done in computing, and they actually have a computer science society within IEEE that does on that, but that you'll see a lot of your standards on stuff are IEEE ones. So when we talk about what the different speeds are for wireless and stuff, IEEE actually is the one that sets the standard on that one. And then they mentioned that there's others out there of the national ones, and they mentioned about the FCC, which is the big one in the United States. And then there's others for other countries all develop these rules too, but they all work together. Now, they want to look at how you actually put the information going across the cable, and they talk about that it's encoded on there. And that is just how do we actually put it out there. And to put it in very simple terms, when you go to put the information on there and you're putting it on there as bits, you're either going to send an electronic signal across or you're not sending, is in the simplest terms. So that if it's a 1, there's something sent. If it's not a 1, there's nothing sent. Or there's a very marginal, or it's a negative signal sent. With Manchester encoding, it sends a negative signal when it is a 0 and a positive on a 1, and so it's distinct on that. Some of the other methods used on that actually rise and fall on it to do, and that it'll stay as a constant level up there. So with Manchester, actually, it drops it back down to that 0 level every time, and that it either sends a positive or a negative on it for a 1 or 0. But in other cases, you'll see it actually stays, if it's a group of binary ones, it'll stay up there as positive, continuous, and then drop. And so, but they only mention the Manchester one to you here. It's not, the Manchester one's not a real huge one for you to be aware of, but just be aware of it. They mention also about how do you send that signal across, whether it's using AM or FM to do it, which is the same thing as radio. That's actually where your AM and FM names come from when you're talking about the radio, is that which way are they sending it? Are they doing a frequency modulation or an amplitude modulation? And so on the AM one, it's a sharp, distinct ones. The FM, it's a movement from one spot to the other, which actually on radio means we get a better signal across in terms of FM. But AM can travel a longer distance. Bandwidth and throughput that they mentioned to you next. Those are two terms you definitely need to know. And there's a difference on them, on bandwidth and throughput. And later on, they'll throw another one at you later in the book. Well, they actually do here, that they mentioned that there's goodput also. But they don't have that as a major item for you to know. Bandwidth, and that's a term you have seen already. You may not have seen throughput or goodput mentioned before. But bandwidth, y'all should have all seen that at this point, because when somebody says about what's the speed of their internet connection they have, they're going to normally talk in terms of bandwidth, and that is what's the potential speed. If you go to Comcast or Charter or whoever and you want to get a better speed on your internet, or you want to just get a connection with them, they're going to tell you in terms of what's the bandwidth. That's the potential speed that it could run. Does everybody follow on that? That's what the possibility is. Okay? On 151 out here in front of the school. Speed limit out there, if I remember right, is still 55 along there, I think. Or maybe it's dropped to 45 there. But in any way, it's got a speed there, and there's a potential that we could carry so many cars across there in a certain time period at that full speed, right? Now, a lot of the day, that doesn't happen. Traffic gets heavier, construction equipment gets in the way, etc., and all kinds of things get in the way, and it may not actually go at that speed. Through downtown Atlanta on I-75, speed limit is 60, I believe, through downtown. That's the potential that cars could go through going through downtown Atlanta. Does that normally happen? No. Okay? And particularly not at certain points during the day, right? But I can tell you, middle of the night, it doesn't always happen either. Okay? So that's with bandwidth. Throughput is what actually is happening. Okay? So if at home you've got a connection that's supposed to be 100 megabits per second, okay, and you go and do a measurement on it, and you're sitting there going, it is awful slow, and you do a measurement on it, and you discover that your speed at that point is only 40 megabits per second. That's throughput. Bandwidth is the 80. Does everybody follow the difference there? Throughput through downtown Atlanta at 5 o'clock is not 60 miles an hour. It's more like about 5 miles an hour. Okay? Same thing on 151 in front of the school. At 5 o'clock, we're doing good if we can do 20 out there. Okay? If any of y'all have been out there on the road at that point, y'all know where it backs up and gets slow out there, right? And we get a few more miles down the road and get into the country, and it speeds up and we can do 55, 60 miles an hour. Or even faster, but not legally. Okay? So throughput is your actual speed that's going through. That stuff is being carried across there. Okay? Bandwidth is the potential. What could it possibly do? Both measured in terms of bits per second. Chart in the book on 153 shows it as B/S for bits per second. I've not ever seen it shown that way. The way I've always seen it is it's BPS. Okay? Now it is a lowercase b because it's bits. If you see an uppercase B, normally you're referring to bytes. Does everybody follow that part? So they mentioned there about it could be measured in bits per second. You're really not going to measure in that today. Although 25 years ago, speeds were measured in bits per second. That a good connection was 300 bits per second. Okay? Now, do y'all want one of those connections? At 300 bits per second. And then kilobits per second, which dial-up used predominantly, and so you see that one's still in use because dial-up's going to just get you up to 56 kilobits per second. Megabits per second, which is where y'all are seeing most of your internet connections measuring in today. And then obviously you got gigabits per second, which we see some having, but most people not having, and that could be in terms of 1 or it could be 10. Downtown Chattanooga now has 10 megabits per second. And actually you've got stuff to work with some other connections, not out onto the internet, but internally to speed things up in some places. And I know at SunTrust Stadium that they've got things running at 40 gigabits per second. Because they had to go with Juniper equipment because, and everything else they got in there, but for their outside connection they had to do Juniper instead of Cisco, because Cisco just could handle 1 or 10, and Comcast actually got them where they could get 40 in there. and Juniper was the only one that had the equipment to sell to them. Cisco will tell you that they can sell you anything, but they couldn't sell them that one. And I don't think price was really an object on it, because they actually spent a ton of money on those 4 boxes, I think it was, that they told us they had there and showed us when I went through SunTrust last summer. But they've actually got that speed into there, and they need it because they're running all their wireless connections, because everybody fan in there can connect onto their wireless, and it's going out that same connection along with their broadcast of the game, etc., going through that connection. So they need that speed on it. And then terabits per second would be the next one. Once we get to 1,000 gigabits, will be terabits. I have not seen anything that's really referenced terabits, but they'll know enough on the computers and communications to know within a few years we're going to be bumping that one. Okay? So you do need to be learning that term there at this point, although it's not out there for you to use yet. You need to at least learn the next level where we're aiming for. And rest assured, Cisco, Juniper, Comcast, all of them are working on trying to figure out how to do it and do it at a reasonable cost. When you're looking at throughput versus bandwidth, one of the things that you've got to consider about is latency is the big problem. Now, all latency is delays that occur. Okay, so when I drive through downtown Atlanta, that's latency when I got to slow down for all of the traffic stopped in front of me. I've now been delayed on getting to where I'm going. Does that make sense to y'all? That's all that latency is those delays. And delays can be out there for all kinds of reasons. Your equipment could be slow, it could be way too much traffic on there, which is what downtown Atlanta's got, etc. Could be a wreck that's held everything up, and that's even on your communications channel, that you could have had collision between transmissions, in which case you had a wreck on there, although that's not the term for it. You had a collision is what their term is. So definitely know what latency is. And then goodput they mention, and what goodput is, and throughput measures everything going across there, whether it's stuff that doesn't arrive in full format, damaged or whatever else, it's still something went across, so it counts it. Goodput only counts the stuff that actually was good received. So if it's got to be sent several times from one device to the other device, it's going to take in account that whole time period that it took on it, from it when it first tried to send it to when it finally arrived. Y'all follow on that? And so goodput is what really got there in good shape. And if you think about out on the highway, not everybody that pulls out of the parking lot successfully gets to where they're going. It's a high percentage of them get there, but there's a few that don't get there, right? Which is what they have the nice little signs up telling us about how many fatalities we've had this year, or all the wrecks that stop people from getting to that point, and that they have to try again. So that's what goodput is. Goodput's what is the speed it really is running at. Okay? Throughput is what it's trying to run. It's basically running at, but it's counting everything going across there as going across. And bandwidth is the potential of how fast it can run. So bandwidth is what Comcast is going to tell you what your connection is, unless you tell them you need to know what the throughput is. Does everybody follow on that? But if you go and measure the connection with speed test, one of the speed test programs, speed test is one of them, it's not going to be measuring bandwidth, it's actually measuring for you at that point throughput. Does everybody follow? And most, if not all of you, should have used one of those speed tests at this point and realize what it will do for you, and that Sometimes that's useful information. And if you're running a network, you may want to regularly run that and see and record it and see how your speeds do, and notice if there's time periods that is slowing down and that you need to work on ways to speed it up. All right, the next so much part of the chapter is going to go into the media and talk about the different types of physical media. They don't spend a huge amount of detail on these, but they're going to talk about different ones. And actually what we did the other day, couple of days in here, fits right into this section here. So when we were doing that lab in class, that really did belong right here. So the first one they talk about is the copper media. And about that you could use copper to send the information across, which is where we really started from as far as doing communications. Still is a predominant way of sending information and will stay out there heavily used. Although the other two of fiber and of air are going to wireless are growing more and more important, but copper is still going to be there. It's sent across as electrical pulses, and that so one device is sending it to the other. Now, when you're sending it across down there on copper, you have several things that can mess up and your signal going through and slow it down, etc. to it, and give problems on getting the signal from one place to the other. They talk about EMI, electromagnetic interference, and radio frequency interference, which is RFI. EMI is going to come off of things that are like the fluorescent light. The ballast up there gives off EMI. So if you're running cabling across, you don't want to run it across tops of fluorescent lights. You actually would like to keep it a distance from fluorescent lights, because it is giving off an EMI, an electronic magnetic signal, which then interferes with what's going across your wire. That's also the reason you want to make sure, when we were doing the plugs the other day, you want to have that sheath go all the way into the plug, because if that sheath will help stop some EMI and RFI. Does everybody follow on that? Now, the other part is, if you've got a whole lot of it around, you may well want to go to shielded twisted pair instead of unshielded twisted pair, because that gives another shielding to sort of block it out of there. But it's still subject to it. RFI is radio frequency interference. If you're close to a radio station, is one place it could be. And if you thought about where you listen on your radio in your car or whatever, there are sometimes stations will bleed over stations, right? That you can end up hearing parts of two different stations at one time. They run into RFI at that point. The other part is motors will give off RFI also. So when you run cabling in plants or where there's some type of motor around, you got to be careful on that, of trying to keep distances and sometimes shielding to keep it out of there. They say it's shown in an illustration, but it's not. They don't even have one there. That's weird. But it will mess your signal up and get it where it actually is not recognizable of what the signal is. Sometimes it just makes it where it's harder for it to catch it and doesn't always catch it correctly. Any questions on EMI and RFI? Those are two you need to definitely be aware of, okay? Microwave ovens will give off them also. Crosstalk is actually where the signal on one wire is detected by a signal on another wire, because when it sends that signal down the wire, it doesn't stay just in that wire, which is how you can actually wiretap wires, okay? That you're not actually breaking the wire and getting it, but you can get close to it and pick up a signal around the wire. Does everybody follow on that? Now, the better we've got the cabling done, the less that we'll have. The other part on crosstalk is, if you don't do the cabling do the wires exactly like I described to you how they should have been done when you did them in the plug, and if you end up with the send positive signal going down one wire, but the send negative signal going down another wire, and so you've got two different things wrapped together, they will end up catching each other's signal some, and that's crosstalk. It can come between pairs also, which is the reason for Cat 6 now versus Cat 5. And since I forgot to bring the cables with me today to show you, I can't show you what the difference is on the 5 versus 6. But what happens with, you've worked with 5. You had 4 different pairs in there, and I don't know if y'all noticed, those pair, inside each pair they're twisted together. So the 2 wires are twisted together. Y'all definitely know that because y'all untwisted those. But the other part is, each of the pairs, those 4 pairs, they wrap around each other. Do y'all follow on that one? And you might have caught that, you might not have. If you didn't, catch it now. Cat 6, and that actually can have canceling out to keep it from being subject to all the interferences we're talking about here, those interferences and the crosstalk, if they're correctly done, because then they keep their signal more tight to themselves. Okay? With Cat 6, what it does is it puts a plastic trough in that cable and keeps the 4 pairs physically separated by a piece of plastic between them. Y'all follow on that? So you got a piece of plastic going through there. It's got 4 different channels on it that the wires lay in. It's got twisting built into that trough, and that keeps them separated, and so that keeps your crosstalk down on it, because now there's a separation between each of the pairs. Does everybody follow on that? So Cat 6 can run faster than Cat 5. Okay? Cat 5 is really designed, and it's actually, when I'm saying cat, it really is an abbreviation for a category, but you're going to see it called cat all the time. That you've got Cat 3, Cat 5, Cat 6. There is a Cat 7 spec out there, and there's actually a specification for Cat 8 and above out there too, but there is Cat 7 cable out there, but I'm not, other than I think it changes the twist a little bit to it, it's not a significant difference, and you don't see Cat 7 really used out there. At this point in time, most stuff is done either as Cat 5 or Cat 6. When this building should be all Cat 6 in it, but I don't know that for sure because I haven't crawled up in the ceiling and I wasn't here when they cabled it. Over at the Walker campus, it's Cat 5 wired through the building, except for going to the wireless access points, because they just did them a couple of years ago. The cabling to the wireless access points is Cat 6. And so when I bring in my cable to you to show you, actually a piece of Cat 6 I've got to show you came from when that was done, because the contractor that came in and did it, I saw what they were doing, what cable they were using, and I went, ooh, can I have a piece of cable? And he said, yeah. And he cut me off a piece of Cat 6 cable for me to have as a sample. He would have given me a lot longer if I'd wanted it, because he said, how long do you want? And I said, well, I just need a piece long enough to show y'all in class. I already had a piece of Cat 6 from back in about 2000. It was definitely before July of 2001. So I think it was 2000. I'm still see the person that gave it to me. One of my students got it from a place they were cabling an office in Athens, Georgia, that she worked at, and that they had just wired the whole off us using Cat 6 cable, which was way ahead of the game back there in 2000. They were doing very leading edge technology in that place there, and she picked up a piece and brought it to me for it. But mostly we're using Cat 5. You'll see it as Cat 5e also. Cat 5e just puts more twist into it and allows it to run a little bit faster. So a lot of the time now what's Cat 5 cable is really Cat 5e. It's enhanced is what the E is. Okay? you'll see a lot of projects being done with Cat 6, but you're still seeing a huge amount and a large amount of the cabling being sold out there is Cat 5, and that a lot of things are being 5. So it's 5 and 6 primarily now. And that's in the twisted pair cabling. Most of it being unshielded twisted pair, just like y'all worked on the other day. And this should be Cat 5E. Yep, Cat 5E, UTP cable. So that's what you're using in most cases. And so y'all have used the Cat 5E UTP at this point. Speed that you can have travel through it, generally they're going to say 100 megabits per second, but it will handle 1,000. Okay, so you can actually run gig on it within an organization. Does that make sense? If you're going to go faster than that, you need to go to Cat 6. And that's the reason for go ahead and do 6 now, even if you're still only running at the 100 on it. Okay? Go ahead and put it in, and that way, as you increase your speed, you've got the cabling. You will see Cat 3 cable still out there. It will only run up to 10 on it, megabits per second. But what it's used for primarily when you see it out there now is that a lot of telephone cabling will actually use Cat 3, although places that are putting it in new really ought to be putting in Cat 5 or Cat 6 to use for the telephone too. Telephones only use 6 of the wires, where your data uses 8 wires. But if you will wire it with Cat 5 or Cat 6 to do your telephone in there, then if you decide you don't need a landline in there any longer, that wire won't be unused. You can just switch your plugs on it from RJ11 to an RJ45 female plug, and it'll work for your data connector also right there and give you another data port for you. And the other part is, if you go to using IP phones, that's what you're going to use anyway. So if you're going to cable someplace and they want to do telephone cabling in there too, you really ought to go ahead and pull them 5 or 6 for the telephone too. Distance on a piece of wire with the UTP STP cable is going to be 100 meters is the maximum length you can go between devices. If you're going to go further than that, you need to put a relay on it to regenerate it and send it further. Everybody follow on that? 100 meters is approximately the size of football, the length of a football field. Or if any of you are soccer players, that's actually the length of a full soccer field. Because 100 meters is going to be about 100 yards. It's actually a little longer than that, which is going to give you about 300 feet, actually 320 feet, I think it is. Shielded twisted pair just has shielding around the outside of the 4 pairs, so that instead of just being plastic there's a little metal wrapping inside of it. It'll work just like you did with the unshielded. It's going to work a little better. I have seen shielded twisted pair and considered also at one point that I considered using it, but I've definitely seen it where it's run through manufacturing plants to reduce the interference coming off the equipment. They did talk about coax. You're not going to see much of coax anymore, but it is still out there. Your cable networks and stuff are using it still and have it for at least coming from the pole to your device in the house. Okay? And although you may have fiber to the house, as they'll mention in just a moment, which is FTTH. Or you could have fiber to the terminal where it actually runs fiber all the way to your little box inside the house. which is what Google likes to put in where they're doing fiber. Although Google has just announced they're backing out of one market, which is Louisville, Kentucky, that it just did not work for them there, that it was laid wrong when they had the fiber laid all around the town for them there, and that it's not running at the speeds it should be running at, and they decided that either they were going to have to redo all of the work again or just drop the project there, where it works in other communities for them. But it just wasn't done right up there. And then they had all kinds of fights of where they could run it. When they tried to run it across poles, AT&T pitched fits on that and sued them and stuff, although they ended up with the rights to do it. And then, so they ended up with a mess, and they just announced this week they're dropping out of Louisville in the next few months. They're going to continue to run the service for, I think, 3 or 4 more months, but everybody that's already on it, they're just going to run the service for them and not charge them anything, and then turn it off at that point, unless somebody else comes and buys that whole setup from them. But they said they really, because they said there was all kinds of problems with the connections done. The fiber optic was not put underground like it should be always. There's people that the report I saw said people would complain about the fiber optic ran above ground, which is laying across the ground. They'd trip on it. Well, with fiber optic, that don't work because you'll break the cable and everything. So apparently they had a mess up there. But coax is out there. Coax has an outer sheath around it and then has a little metal wire down the middle. And so they illustrate that one to you. So it's got a copper conductor in the middle that actually carries the signal, and then it's got a ground around it that is that shielding on it. And when we were looking at the strippers, that was where I made the comment about you had the 2 blades on it so that you could cut the 2 different depths on it. It's got an outer jacket on it, and then they mentioned there to you about that plastic insulation. Actually, where they've got that described as plastic insulation there, or on the previous, on another page somewhere in here. Yes, they don't. It's a lot of times is not plastic insulation there going around the actual little wire in the middle before they put the outer metal sheath around. A lot of times they use Kevlar right there to reinforce it. So what's Kevlar used for? Body armor. It makes bulletproof clothing. Okay? Because it's got a flex to it that other fabric doesn't have to it. And so it can block the bullets and stuff on you. Well, for here it works because it keeps when the cable gets hot or whatever, it keeps it from being stretched as much. It supports it better and gives a better support to it. So they'll use Kevlar literally there on it. Don't think they mentioned that to you in the book, but that's what you'll see. And then the outer part is just to protect it all. Because they just say plastic in here, but Kevlar is what's used a lot of times. But so they mentioned to you about those. They mentioned about the connectors, but there's not much mentioned there to you. The B and C connector, just to mention that one to you, which is a very common one on it, is actually the BNC. There's questions on what it stands for, but most people would tell you it's British Naval Connector. Exactly how they came up with that name for it, I never have figured out, but that's there. And then they got the N-type and F-type. F-type is the one I've seen between the BNC and the F-type is probably the 2 most common. BNC for data connectors, if you're looking at like your cable network connectors and stuff, a lot of times those seem to be using the F-type. If you're working with copper, the other thing is to be fully aware of, it is copper and will carry electricity, so you don't want those bare wires of it laying up against electrical wires. And you really don't want it running right beside electrical wires, because it will, if it at all gets some exposure, it can grab that electrical signal and carry it right through your data wiring. Your data wiring's only carrying like about 12 volt signals across it. 5 to 12 volts, and if you drop 110 volts onto it, you're going to burn some equipment up. Okay? So you want to protect it on that. And just also be aware that if it does come in contact with it and somebody is handling the wire further on down, it's a good way to get them electrocuted. They then go through and talk some about the UTP cabling. And I've already talked pretty much about this stuff. They show you the connectors on it. Y'all know how to use your regular plug, the male plugs. The female plug is pictured for you there also on page 165. Basically on that, you're going to undo all of the little wires, and then there's a specific spot that you just push it down into. You're not having to go and do all of the work that you have to do to get the male plug on there. So you just push it into there and it makes the contact, and you just push down on it. I'll try to remember to bring one with me and show you all on that. But it is color coded on it, so it shows you exactly which one goes in which position. Does everybody follow on that? So it's simple. If you know how to do the male plugs, y'all can figure out how to do the female plug when you see one. Okay? That you just run the wire in the middle and separate them out and push them down the spots. There are little tools to punch them down, or you can use just a small flathead screwdriver and push the wires down into positions. Questions on that? And then they show you a little on how to do it, show you their illustration of doing the straight through, crossover, and rollover. And remember, the illustration in the book's not a good one. The one online is a good one because it's in full color. And then they talk about fiber optic a little bit. And we're going to be out early today. Big advantage of fiber optic is it is not subject to interference on EMI and RFI. It is a light signal going through there, so other type regular signals out there aren't going to interfere with it. So you'll use fiber optic in some cases at places where it's highly susceptible to interference. The other part is fiber will run a whole lot faster than copper. So you're using fiber to run all over the place and for backbone, etc. on it. And that where they mentioned about fiber to the home, it's actually, most of the time it's actually fiber to the pole. And it just gets you fiber out there to the pole on it, although it's buried, so really poles aren't poles now as far as fiber is concerned, but they've just got the little box that sticks up, and they may run it up the pole then when it goes to copper at that point. And then like on the case of the one in Louisville, they were using the acronym of FTTT for fiber to the terminal, is the way they were trying to do it. So if you see the acronyms, you guys play with it accordingly. With fiber, there is a little glass tube in the middle. It could be plastic or it could be glass. Corning, that used to make all the Corning pots and stuff, they're actually two separate companies now. They got into making those glass tubes, and then they spun off the company that makes the cookware stuff. Is that you've got a glass tube through the middle, then you've got cladding around it. That cladding there will almost always be Kevlar, because you don't want that glass tube at all to stretch or it'll break the glass, because it breaks just as well as that window right there will break. Because if he gets up and off and hit with his fist, what's going to happen? We're probably going to have an outside opening at that point, right? And then it's got some plastic around it. The strengthening material actually sometimes can be the Kevlar there, and then it's got plastic around the outside of it. Big parts of it is that it's got the cladding on it, and that it's got a glass or a plastic tube in the middle. And it could be glass or plastic. The glass is actually going to run faster. Okay? the glass is harder to work with, so you have to be careful with fiber. You can't bend it too sharply or you will break the glass in it. The plastic tube will break also. Depending on if you're using a laser to send a signal through, which will be on single mode, and it just sends a single light signal down the middle of the tube, or it could be multi-mode, which normally uses LED to send it, and it actually sends multiple signals through at the same time, but angles them differently, and it bounces it off the walls of the glass or the plastic. Y'all make sense on that one? So each of the signals is going at a different angle, so they don't run into each other because they're bouncing separately on it and go through that little tiny narrow tube that actually most of the tubes are too small to run one of your hairs off the top of your head through. Although I don't think any of y'all got hair that's 10 miles long for us to run through it. So it can use laser. Could you use LEDs? The laser one with the single mode is going to run faster, because when you bounce it off on the sides of it, you are going to have some dispersion occur as it goes, so you can't run it as far and you can't run it as fast. Okay? Does that make sense? But you're running it at the speed of light, but the laser is going to run a faster speed on it and get it through faster on it. Distances on fiber can run anywhere. They give you up to, they give you 100,000, I think, or something. They actually run it longer, up to 100,000 meters. Biggest I've usually ever seen them run, that anything listed at running most of the time, is usually 10,000 meters, which is going to run you about 6.2 miles. Because if any of you are runners, I know that one. Because there's a lot of races at 10,000 kilometers on it. Not 10,000 kilometers, but 10K or 10,000 meters. And it's about 6.2 miles. And that's what we've actually got running, the single mode running between campuses as our connections. And they talk about the connectors in here also. They mention about 4 connectors there: the straight tip, the subscriber connector, and then the Lucent simplex connector and the duplex multi-mode connectors. The straight tip and the subscriber connectors, the two that you'll see mentioned most often, ST and SC. To put those connectors on there, most of them will require you have to carefully cut the fiber optic cable, and then that you got to sand down the edge, because you got to because the glass is going to splinter slightly even on that little tiny thing, and that you actually sand it to smooth it back out, because you don't want any imperfections in it there, because if that light catches an imperfection, it changes how the light goes. And then you epoxy on the connector on there. However, there are other connectors out there now, and that was the way it was done originally for a long time. Now there are connectors out there where you don't have to go through doing the epoxy type approach on it. I was shown how to use it using epoxy at one point, but it was more of a demonstration. I actually did a couple of connectors on it that day, but we didn't really get into it very well where I would ever feel comfortable when I walked out that day of doing any others. But I knew about how to do it, which was what my object was that day. And that was what the instructor that was teaching me and 2 other instructors that worked for me at that point, he was just wanting us to see how it was done and have done it to have a feel for what happened, but not to be ones to doing it. So you've got to have a higher knowledge level to do fiber. Cable, the copper cable is fairly simple, as y'all saw already, and that you know how to do that one. Patch cables, I'll show you on that quite often, as it says there, orange for multi-mode is usually the usual mode, and then yellow for single mode fiber cables. I don't have any of the single mode to show you, although what goes along down on the road out there would be single mode, so I actually do have some single mode on that, because I've got a piece that one of my students gave me last semester, I think, or the semester before, that works for one of the companies around, brought me a piece of the multi connect wires through it for me to be able to show people, because all I had before was just 2 single fiber wires together on a connection, which is what I used back in the early 90s, connecting up buildings on a campus where I was setting it all up. I didn't install the fiber. We brought in a contractor to do that, but to do the connection from building to building. And then within the building it was all copper, and I can handle that one. It uses a different meter to work with on fiber, and actually when you use that meter, not only will it tell you in terms of is it set up correctly, but if there was a break in the fiber at some point, it will tell you how far down the line that break is, which, considering most of your fiber is buried underground, that is significant to you, because then you can go find the spot to go dig your hole to get in there. The other advantage to fiber, besides it not being subject to RFI and EMI, is it's also very difficult to eavesdrop on. It's not putting any signal outside of the tube. The only way you can eavesdrop it is you've got to cut it, put the connectors on it, and put a box in at that point to catch the signal. At least up till now, that has been the thought. Now, some things I have read in the last month claim that the Russians have some box created that they use on some of their subs, that supposedly when they get close to fiber, that they can actually listen, catch some signals of some type coming off of it and listen on. Now, whether it really can occur or not, who knows? But that's what their stories on, claiming there's an ability to do that now. I've got my doubts on it, but it may be. I'm seeing too many stories saying they think it's occurring, and there's too much stuff coming out saying, so I'm thinking it may be occurring. But my thinking still is, which has always been this before, was that you couldn't eavesdrop on it, because the only way you could eavesdrop was you had to cut the cable, put new connectors on, put a box in between. Well, guess what you've done in all that time? You cut that cable, put the connectors on, and connected it to a box that then transfers it through. You've set off alarms on both ends of that cable, telling them that there's a break in the cable at that point. Okay? So they know something's going on out there. So it's not, as opposed to like with the copper, you can just get close to it with devices and pick up a signal off that copper without breaking it or anything else on. But with fiber, you really got to break it, and it's going to set off an alarm that stuff's not going through the line anymore at that point. And then when it reconnects and you haven't sent somebody out there to fix it, that should set off some more red flags that you should be going. Questions on that? Speeds, they mentioned that it could run anywhere. Fiber, it says it could do at 10 megabits per second, but you're not going to run it at that speed for sure. And it says up to 100 gigabits per second, and actually there's stuff saying we can go faster than that. Now, realistically, out there at the current time, maximum speed on fiber is 40 gigabits per second. You've got some things running at 40. Like I said, what they're doing, Comcast dropped to SunTrust. But like if you go to downtown Chattanooga, what they've put down there is that the newest stuff is at 10. And most places, if they can get 1 gigabit per second speed, that everybody's saying they got extraordinary speed at that point. But now 10 is really where a lot of stuff's moving to. And then there is the potential for 40 that is actually in use, but very, very limited use out there. And so they got a fairly good chart on that one. Then they go into wireless for you and talk about that one. Some things about wireless. One is your coverage area is limited. And depending on the speed and which bandwidth which type you're using there will have an effect on it. Because if you're using the latest one, you've got where it runs at running on a 5 gig transmission, that it runs closer but runs fast on that, but then to get a little further out that it drops it down onto the 2 on the megahertz. So remember what I'm talking about. So 5 megahertz or 2 megahertz, the 2 megahertz will get further, but the 5 megahertz will go faster, but you're limited closer. And with your AC standard, you're actually doing 5 close up to your transmission point, and then when you get out to a certain point where it drops off, it does a sudden drop off, that it switches itself to 2 from that position on out and gives you some. So you're limited on that. The other problem is building materials, etc., will block wireless also. And you actually do have buildings being built where they don't want the wireless to leave the building, and so the outside of the building has got a metal outside to it just to keep the signal inside the metal building. And that even if they put up a brick building, they may put a metal shield behind it for a purpose of limiting the wireless from leaving the facility. Does that make sense? Actually, if they put a mesh up on it, would do a better job on it. And so that you'll see too that they'll do it. If they want it to be a secure building, they'll put a stucco surface on it. Because then you can put a metal mesh up on it, put the stucco on that metal mesh, and it doesn't look strange or anything to everybody, and that metal mesh will kill a wireless signal. Church that I do stuff with in South Georgia, that I tried getting wireless into the sanctuary there. It was built in 1953. When they put up the walls in the sanctuary in it, they did not use sheetrock putting them up. They put real plaster walls up in there, so they put basically chicken wire up on it and pasted plaster onto it. I couldn't get a wireless signal to go into it for the longest time and kept trying to figure out why couldn't I get the wireless signal to get into that room very well. And then when they went to remodel it a few years ago, that a guy told me right afterwards, I had been in there while they were doing some extensive remodeling, he said, told me that it was wire mesh plaster around it. I went, oh, that's why I can't get a signal through on it. Now they've actually got a wireless transmission in there because the local cable people, there was another cable company came in and they said they'd put it into the church and supply them a free connection up there on it, which works real good for transmitting it out, because now I send their service out on Facebook Live. So they mention security. Wireless is not very secure at all. Fiber is your most secure communications channel. Wired next, and wireless the least secure. Interference, lots of possibilities on interference with wireless. And the more interference type stuff around, the least distance you can get from the transmission point. Okay? Things to consider on it. And that wireless is a shared medium where you got lots of stuff being all transmitted all at the same time. They mentioned about the standards on it. 802.11 is the big standard on it, which comes from IEEE. The latest one that we're using now is the 802.11 AC. We've gone through A, B, G, N. Am I skipping one before AC, or is N the last one before AC?
Are you talking about the wireless connection?
Mm-hmm.
Is there a G?
A, B, G, and N, and AC.
I think that's it.
There wasn't one between, for some reason in my mind, I keep wanting to put something between N and AC. But I've got AC at home, and I've had AC at home for several years. I had AC when it first came out. I found some cheap equipment. Bluetooth is another one, which is 802.15. When we talk about Ethernet in the next chapter, we're going to see it's 802.3, which is actually normally running across, well, it used to run across your twisted pair, but it's running across through your wireless too. And then they mentioned about the WiMAX. So that gives us broadband access instead on it and faster. And that one, the number is not quite as significant to you of 802.16. 802 is your communication standards of data, okay? And then they show you a wireless broadband router, and this one happens to have 2 antennas on it, and that was actually not a home one. They mentioned the wireless access points again, the wireless NIC, which y'all saw one of the other day because I got it out of the machine back there and showed you. Questions on wireless? And wireless is going to make more leaps and bounds forward because it's gotten really heavily used out there. All right, then they talk about the data link layer and about the 2 subnet layers on it of the logical link control and the MAC. The MAC is really more what we're looking at in this chapter because that's the part that gets dealing with the physical type stuff. And so it associates down to the physical layer. The NIC fits into the MAC. The MAC uses the MAC addresses. And then talk about the frames in the chapter. So they give you a brief thing about topologies again, both in terms of the WAN and the LAN on it. So they show you those, and that's just how are we, if it's a physical topology, how are we actually got all the devices connected together. Logical is how it could be working differently from within the devices. So they mentioned about the mesh network where everything replicates itself all over the place, duplicates itself. So they did give discussion on several different topologies. The LAN topology, they mentioned about their star. That's where you've got one central device and a bunch of devices coming off of it. Physically, you'll see star a lot of times used. This is actually a physical star here in the classroom because you got separate wires going all back to the switch sitting down the hall. Logically, it is a bus network because actually within that switch, the signals running up and down it to all of these devices. But physically, it appears to be a star. And then a ring, we'll probably mention later in the book, but that's a specialized one. It's not used much anymore, but FIDI does use it. Token rings pretty much disappeared. And that's where all of the devices sit in a ring around, and it shares the information going around, but it goes from one machine to the next machine to the next machine. Whereas on the bus, it goes to every place along the line. Half duplex, full duplex. Half duplex says that we're sending or receiving one thing at a time across. Full duplex says we send and receive at the same time. Give you examples that y'all can associate with on that one. Telephone is a full duplex device. I can call him, and we can both talk to each other and hear each other at the same time, right? Half duplex would be if we would decide to use a walkie-talkie or a ham radio. I can talk to him and he can hear me, and then he can talk to me and I can hear him, but if we both try to talk at the same time, neither one of us hear the other one. Does that make sense? So you can only do one direction at a time. So that's the difference between those two. They talk about the access control methods, and they mentioned about contention-based access and the controlled access. Contention-based access is what you're going to normally see in use out there today. Controlled access, if you found a FIDI network, which some hospitals still use FIDI. Token ring also used controlled access, but you're really not going to find much of that anymore. But you will find FIDI out there in some hospitals. What happens with controlled access is each device can only send when it's their turn. And they will pass a token between them, which is why it's token ring. And FIDI's actually token ring on fiber. Okay? And a machine can't send to anybody else until it gets its turn. So, everybody follow on that? And so, you guaranteed everything's going to arrive that you send out, but you got to wait your turn to send. Now, if that's not you as a user, you go ahead and hit send. But how soon does your machine send it out is not until its turn comes to send it. Everybody follow on that? With the contention-based, it says there that all nodes operate in half duplex. Actually, full duplex will work on that, and that's where we've moved to, is to a full duplex on it. But with contention-based, it sends it out there and trust that it's able to send at that point. So then they mention about within contention-based, there's CSMA-CD and CSMA-CA. And actually, as we go into the CA, that's where you're getting more into the full duplex. And also the CA is used with the wireless, where CSMA-CD is used wired. CSMA-CD, carrier sense multiple access, is what the CSMA is. You're doing multiple machines all connected on the same wire, and you're doing carrier sensing of whether or not stuff's on there. CD stands for collision detection. Machine, you hit send, hit enter, or click the send button on the screen. And the machine then, if you're using CSMA-CD, the machine goes ahead and sends it. Okay? But what it will do is, it will look and see, do I see a signal right now? If it doesn't, it sends it. Now, that doesn't mean some other signal couldn't be coming along that it didn't see as it went to send. And they'll collide with each other. You have a collision occur at that point. If that happens, just like if two cars run into each other, that we have pieces of cars laying around, we have fragments of cars, on the media, on data communications, your frame will actually break apart also, and you got fragments of frames floating on the wire then. The first device that sees it will immediately send out a signal and say, whoa, we've had a collision, and broadcast that across the network. All of the devices will stop sending at that point, wait a random amount of time each one of them, and then try sending again. And anything that they knew they hadn't gotten confirmation back on, or it hadn't been enough time for it to get there, it will resend. All of them wait random amount of times so they don't all go try sending again at the same time, so that won't work, right? So they got a random generator for a time delay. And then they keep on sending. Your object is to keep number of collisions down to a minimum on CSMA-CD. You're not going to get them reduced to zero because of the way it works. It just looks and sees, is it clear right then, and proceeds to go. It's sort of like if we go out in the parking lot out there when we get out of class and we all get in our cars. I look back to see, is there any car behind me at this point? I don't see a car behind me at that point, so I put the car in reverse and proceed to back up. Now, what could have happened in the meantime from the time I look to see if there was a car behind me, and I start backing immediately? He's driving on by me at that point, right? So what do? I backed into his car. So now I got him mad at me. But maybe he wanted to get rid of that car, so maybe he's happy with me. That's with collision detection. Does everybody follow on that? I gave this lecture one day in class and had two ladies sitting in the class look at each other and just start laughing when I started describing that. And describing it like I just did. And I'm thinking, what's going on? Well, at the end of class, they came up to me and told me. One of them had managed to back into the other one out of their driveway, apparently just about using that approach. They were clear when she got in the car and she went to back out of the driveway, and the other one was driving by and got backed into. Because you really want to look both directions and keep on looking, right? Collision avoidance takes a different approach. Either you have to wait for your turn, which is what we mentioned back there about token ring and fiddy, or it sends out a signal, and it's used because wireless will use it, sends a signal and says, I am going to broadcast. I'm going to send a signal at this point. Is it okay? So it sends a signal and says, is everything clear? If anybody's sending at that point, they'll send a notice and say no. And so it doesn't send it. So it waits until it sends out a signal saying, I'm going to send a signal, that I'm going to send information. Is it okay? Until it doesn't get a response back when it sends it out in the short amount of time it knows to wait. And then it sends it. Likelihood of collisions occurring in that is very minimal. Does everybody follow? Because you've sent out a thing. It's now, to use our two cars again out there in the parking lot, instead of me getting in the car, just looking behind and then backing up, I proceed to send up a rocket flare to say, I'm going to back up. Okay? And if he's going to be driving right there, it's right there where he's going to drive right by me at that point, he lays into the horn at me at that point, right? Of don't back up. Theoretically, the backup lights work the same way, although we know too many people sit out there, put the car in reverse, and then just sit there for a while. And so the white lights on the back of the car doesn't always tell us they really are going to back up. It does tell us to be a little more cautious at that point, right? So that's really using more of the CA on it, because there's signaling that they are going to back up so that the rest of us know not to be right behind them at that point. Does everybody see the difference between the two? So with CA, you shouldn't have collisions. You've got too many devices hooked on there if you do have collisions. CD, you are going to have some collisions, but your object is to keep your number of collisions down to a minimal. So if your number of collisions starts growing up too big, you've got too many devices on the same segment there, and you need to resegment your network further and split your broadcast domains. Everybody follow on that? All right, then they go through and show you the frames and mention to you what's typically in a frame. So they mentioned there's a start bit and a stop bit, or it calls it a start and a stop flag. And all that is a bit going through saying, or it could be several bits, but usually they just say a start bit and a stop bit. It's a bit to say, here comes the frame, and a bit to say, there went the frame. Sort of like that they've got an engine on it, like on a train, and then where we used to have cabooses marked at the end of it, or the little red light that they stick on the last car now, so that you know here's where the start of the train was and here's where the stop of the train was. In this case, here's the frame starting coming at you, here's the frame stopped. You got all of the frame at this point. Okay? Addressing, we mentioned that the other day already, but it's going to have MAC addresses on there that's going to give you the physical address of the machine it came from and the physical address of the machine it's aimed for at this point. Type is just going to tell you about the type of the data that's in there. And it says it's a layer 3 protocol on that, so that's telling you what's encapsulated within the encapsulated in there. And then the control one actually tells you how's the priority of this message to other ones. Voice over IP packets, they mention normally have a higher priority than other, because with voice over IP, it's critical all of the stuff get there more quickly than in data. Although, in medical units and stuff, that's another reason for using FIDI and them, is to make sure everything has a high priority on it, because stuff that's traveling across the data network in a hospital environment quite often is critical on it. If you're laying there in ICU and you've got a heart monitor sitting on you and your heart quits beating and it sends a signal to the nursing station that your heart's not beating now, you want that to be a high priority message going to the nursing station, right? So there's that to play in it. And then there's the data that's all in there, which actually is your packet that's encapsulated in there. And then there's also an error detection field normally on there where it does a calculation of that whole frame, comes up with a number that represents it, and attaches it. At the other end, it does the calculation again, comes up with a number, compares the two numbers if they're the same. Then you can reasonably expect that everything got there in the frame, intact. Now, I said reasonably. It's not 100% reliable. And that there is chapter 4, because I just hit a blue page. Took a little longer than I thought it might take, as we are an hour and a half close to. Any questions on it all?
The control and access in figure 4.
What?
Control and access in figure 4, where you have to take turns with computers. Can you put it in reverse? Like, let's say one computer's isn't there, and it can't reply.
It's going to go in a specific order around on them. It always, the first, and it has a token with it. To illustrate it as an example would be to take turns talking here in class, that at this point I've got this device and only the person with this device in their hand can talk. I can talk as long as I got it, although on that you only got it for a designated time. Then I hand it off to him. At that point then he can talk. I can't talk any longer. And if he's got something to say, he says it right then. If not, he passes it to him. He can then speak, but neither of us can speak any longer until it makes it all the way back around to me, and then I can speak again. Does that make sense? And that's what's going to happen on that one. And so there, if you notice with that whole approach, and it gets to each one, you have your chance to send your anything that you got to send at that point. If you don't, it passes it on to the next one. And so it works efficiently. There are no collisions then, because only one device at a time can send. So there can't be a collision on the network. Okay? Other questions? All right. Then I will let y'all go. You've got tests due on Monday on this. And so that's got y'all set. And then I did do the recording today.